There we go. Let's somehow change my settings. So hello everybody, Daryl Lee Berry Jr. back for some more physics. We'll be doing some classical mechanics today, some canonical transformations. So I'll go ahead and jump right in. And I may actually try a different orientation on my pad here. We'll try the horizontal orientation today. And the topic mentioned in the video title so that's what I'll be looking at today. Let me change the scrolling text there. So I know it has to do with canonical transformations because I found the term several times in this chapter. So we'll go through this chapter and see, and see what I find. I have to remember to keep my pad turned the other way. So we'll see if I can remember that today. And I'll make a slight adjustment on that, and there we go. So hopefully that allows a good view. And I'll just go ahead and keep some really good notes as we go along here. So this is chapter 9 of Goads, and I shall read it to you all. And you'll see the notes as I go along. We'll see how that works. It seems like we're going to get through the whole book. Usually that's the way it is with the tougher courses. You actually read through an entire textbook, even though I can't say I read every page of the book, but read a good majority of it, I would definitely say. Favorite book is still a book on differential equations from my undergraduate. Just well-written book. All right, canonical transformations. When applied in a straightforward manner, the Hamiltonian formulation usually does not materially decrease the difficulty of solving any given problem in mechanics. So the Hamiltonian is something we're learning for this last exam that has to do with the Lagrangian. And I'll pull up my notes here and see if I can give you all a bit of a refresher on the Lagrangian. Pretty sure we did Lagrangian before. Might be better just to scroll through the textbook to go to that section. Here we go. So, a lot of stuff with this new section, but so I'm working on it right now. And let me check and make sure the stream is working out okay. Seems to say that it's okay. Testing. Right. Seems audio is coming through. Yeah, this is good. But with those who pop in, let me know if you all see any issue. Everything seems fine on my end. So for the most succinct definition of the Hamiltonian from my notes from class. I guess I'm not going to find it. So let me just scroll through so I can make sure I get you all the best or the most accurate rendition. So the Lagrangian is a way of getting equations in a sort of complicated way where L is going to be a function of Q, Q dot, and T. These are basically generalized coordinates for the system that we're dealing with, like with a spring, a mass on a string, and it'll be X and X dot as it's moving along the horizontal. And the Lagrangian is going to be T minus V as far as the actual Lagrange function. And there's the Euler Lagrange function, which is d dt, partial derivative of the Lagrangian with respect to q dot, minus partial derivative of the Lagrangian with respect to q, and you can have multiple of these, equals 0. So basically the first thing we do is solve for this Lagrangian, and basically this equation here would allow us to get the equations of motion. And this is from equation 8.1 in the book. Now, one thing we can do first, at least one thing we should do first after we get the Lagrangian, is get the conjugate momenta. And the function by which we get these, P is a common symbol for momentum, is going to be the partial derivative of the Lagrangian, the L of Q dot T with respect to partial Q dot. And the sum is only on I, not on J. So these are J's on the numerator and I's in the denominator. So, and it calls Q and P the canonical variables. So the idea is that a Hamiltonian, instead of having Q dot and T, it'll have Q, P, and T. So in essence, we have to get everything in terms of momentum. So after a whole bunch of algebra and math and stuff like that, the Lagrangian ends up, the Hamiltonian ends up being this: Q dot I, PI, which comes from this, minus the Lagrangian. So this function is what we're talking about as far as the Hamiltonian. I may have missed a few steps up in there. They give a long rendition of steps where the first one is to get the Lagrangian, which is T minus V, the conjugate momenta. So that was right next. Um, get the Hamiltonian, which is here. Um, then we invert to get Q dot, which is functions of Q, P, and T. Then um, manipulate the function to f of Q, P, T. And what ends up happening is we end up getting equations of motion out of this formulation without having to use the Euler-Lagrange formula. So basically we can skip that formula and start using the Lagrangian inside the conjugate momenta equation. Formulate the Hamiltonian, get Q dot, and then manipulate to get an F, Q, and P. And what is happening is we end up getting three Hamiltonian equations, which off the top of my head I don't recall. But they're basically equations that give us um, the same equations of motion that we get otherwise. So that's some background on that. So going back to chapter 9, the focus of the discussion. We wind up with practically the same differential equations to be solved as are provided by the Lagrangian procedure. The advantages of the Hamiltonian formulation lie not in its use as a calculation tool, but rather in the deeper insight it affords into the formal structure of mechanics. So the Hamiltonian informs deeper structure. The equal status accorded to coordinates and momenta as independent variables encourages a greater freedom in selecting the physical quantities to be designated as coordinates and momenta. All right. So it looks like since QPT, none of them have a derivative dot on it, is there's more options to choose from there. As a result, we are led to newer, more abstract ways of presenting the physical content of mechanics, which, I guess is a good thing in the end, but abstract is generally not as workable as explicit problems, even though it becomes more so as you get better at more advanced physics. While often of considerable help in practical applications to mechanical problems, these more abstract formulations are primarily of interest to us today because of their essential role in constructing the more modern theories of matter. Thus, one or another of these formulations of classical mechanics serves as a point of departure for both statistical mechanics and quantum theory. All right? It is to such formulations arising as outgroups of the Hamiltonian procedure that this and the next chapter are devoted. So we know that the Hamiltonian gives deeper structure, and that goes into quantum. Those who've been following and familiar with the quantum videos, we know we talk about the Hamiltonian there. That's directly related. And then stat mech as well, which I'll be taking next semester, the graduate version of it. The equations of canonical transformation. So now we're in 9.1. We're almost to the point of interest. There's one type of problem for which the solution of the Hamiltonian's equation is trivial. Oh my gosh, when they say trivial. Consider a situation in which the Hamiltonian is a constant of the motion and where all coordinates q are cyclic. Under these conditions, the conjugate momenta p are all constant. This is the conjugate momenta. All right. So we're dealing with a formulation where the Q a cyclic, and H constant of motion. And thus we have Pi equals alpha. And since the Hamiltonian cannot be an explicit function of either time or the cyclic coordinates, and can be written as Hamilton's equation for Qi are simply interesting. Q dot I is partial H over partial alpha 1 equals omega 1. That's 9.1. Where the omegas are functions of the alphas only, and therefore are also constant in time, right? So omegas are functions of the thing that's already constant, the alphas. Okay. Q dot I equals omega 1, thus Q I equals omega I t plus beta I. That makes sense because you take the time derivative, Q dot is just omega, the t goes away, and we have to put the constant of integration because we don't know if there was a constant there that went away because it was constant when we took the derivative. And these determined by the initial conditions. It would seem that the solution to this type of problem, easy as it is, can only be of academic interest, for it rarely happens that all the generalized coordinates are cyclic, but a given system can be described by more than one set of generalized coordinates. Thus, to discuss motion of a particular particle in a plane, we may use as generalized coordinates either the Cartesian coordinates or the plane polar coordinates. Okay. So Cartesian coordinates is with x and y. We can say q1 equals x and q2 equals y, or we can say plane polar coordinates. We can say q1 equals r and q2 equals theta. Both choices are equally valid, but one of the other set may be more convenient for the problem under consideration. Note that for central forces, neither x nor y is cyclic, while the second set does contain a cyclic coordinate in the angle theta. The number of cyclic coordinates can thus depend on the choice of generalized coordinates. And for each problem, there may be one particular choice for which all coordinates are cyclic. If we can find this set, the remainder of the job is trivial. I hate them to keep saying that. Since the obvious generalized coordinates suggested by the problem will not normally be cyclic, we must first derive a specific procedure for transforming from one set of variables to some other set that may be more suitable. The transformations considered in the previous chapters have involved going from one set of coordinates, Q, to a new set, capital Q. The transformation equations of the form. So we have Q, I is Q, I of Q, and T. This is 9.3. For example, the equations of orthogonal transformation, or the change from a Cartesian to planar to a plane polar coordinates, have a general form of equation 9.3. As has previously been noted in derivation 10 of chapter 1, such transformations are known as point transformations. Within the Hamiltonian formulation, the momenta are also independent variables on the same level as the generalized coordinates. Okay? The concept of transformation of coordinates must therefore be widened to include the simultaneous transformations of the independent coordinates and momenta QP to a new set QP. Right? So this is the general form. Here we have QI equals QI QP. See, so the momenta is added up in there. And PI equals PI QET. So this is what we have here. And this is 9.4. Thus, the new coordinates will be defined not only in terms of the old coordinates, but also in terms of the old momenta. Equations 9.3 may be said to be definite, a point transformation of configuration space, especially equation 9.4 divide a point transformation of phase space. In developing Hamiltonian mechanics, only those transformations can be of interest for which the new Q and P are canonical coordinates. So that means that when you think if it's canonical, that means that if we're dealing with a vector, the transpose of the vector sandwiching the anti-symmetric vector is still 0. We have this as J. So if it's canonical, that means that if we take the anti-symmetric matrix and sandwich it between the two observables we're working with, it should give us J again. If we're dealing with something that's canonical. This requirement will be satisfied provided there exists some function k such that the equations of motion in the new set are in the Hamiltonian form. All right? So equations of motion new, what do we have? We have big Q dot, our new coordinates, equals partial k over partial p, capital P, and p capital dot equals negative partial k over partial qi. And this is 9.5. The function k plays the role of the Hamiltonian in the new coordinate set. Okay. New coordinate, right? Gives us a asterisk. Asterisk says it has been remarked in jocular vein that each other. Right? Apparently, K, they call it a Hamiltonian. It's a transformed Hamiltonian, but it takes the same, does the same behavior. Let's just say QP must be canonical coordinates, not only for some specific mechanical system, but for all systems of the same number of degrees of freedom. Equations 9.5 must be the form of the equations of motion in the new coordinates and momentum, no matter what the particular initial form of h. All right? We may indeed be incited to develop a particular transformation from small QP to big QP to handle, say, a plane harmonic oscillator. But the same transformation must also lead to Hamilton's equation of motion when applied, for example, to the two-dimensional Kepler problem. As was seen in section 8.5 of QI and PI, there are to be canonical coordinates. We must satisfy a modified Hamiltonian principle that can be put into the form, right? But we need seems to be a delta function. This is equation 9.6, where summation over the repeated index I is implied. At the same time, the old canonical coordinates, of course, satisfy a similar principle. So I'll put and this is the lowercase. Now we see what they mean by being the same form. It literally is the same equation, but just in a different set of coordinates. The simultaneous validity of equations 9.6 and 9.7 does not mean, of course, that the integrands in both expressions are equal. It's a general form of the modified Hamilton's principle has zero variations at the endpoints. And that's a derivation that we did months ago, getting the Lagrangian, how you have a small shift in the line or function, the endpoints align perfectly, and only the middle part is there a slight shift. Both statements will be satisfied if the integrams are connected by a relation of the form lambda. So I guess we're going to have to find lambda. This, I'm recalling something like this from class. Here, f is any function of the phase space coordinates with continuous second derivatives, and lambda is a constant independent of the canonical coordinates and the time. The multiplicative constant lambda is relative to the particularly simple type of transformation of canonical coordinates known as scale transformation. All right, so now we're about to get to the mention of the generating function. Suppose we change the size of the units to measure the coordinates and momentum so that in effect we transform them to a set q prime p prime defined by, so this is an example. So the units are going to q prime I equals mu qi, pi prime equals getting the names of these Greek terms. I think the second one is mu. The first one, yeah, I don't remember the names of these Greek symbols. Then it is clear that Hamilton's equations of the form 9.5 will be satisfied for a transformed Newtonian k of q prime p prime equals uv hqp. The integrands of the corresponding modified Hamiltonian principle are also obviously related, which is the form of equation 9.8 with lambda equals uv. With the aid of suitable scale transformation, it would always be possible to confine our attention to transformations of canonical coordinates where lambda equals 1. Thus, if we have a transformation of canonical coordinates lower qp to capital QP prime for some lambda equals not 1, and we can always find an intermediate set of canonical coordinates QP with no prime related to QP prime capital, QP and both of those are capital, by a simple scale transformation of the form 9.9, such that mu nu, that's what it is, mu and nu. Mu nu also has the same value, lambda. The transformations between the two sets of, that reminds me of an example of a problem or something. You know what? That reminds me of the fission problem from the homework where the leading terms equaled 1. So the leading terms I multiplied that equaled 1 must have been the mu and the nu. I guess I'll have to look at that formula. Such that mu, nu, equal, check on that later. So that it seems like I must have did that problem right. The transformation between the two sets of canonical coordinates Q and P will satisfy equation 9.8, but now with lambda equals 1. Since the scale of transformation is basically trivial, the significant transformations to be examined are those for which 9.11 hold. Right, so this is an important equation. What was 9.11? The transformation canonical coordinates for which lambda equals not 1 will be called an extended canonical transformation. When lambda equals 1 in equation 9.11 holds, we will speak simply of a canonical transformation, which is what we're doing in class. The conclusion of the previous paragraph may then be stated as saying that an extended canonical transformation can be made up of a canonical transformation followed by a scale transformation. Except where otherwise stated, all future considerations of transformations between canonical coordinates will involve only canonical transformations. It is also convenient to give a specific name to canonical transformations for which the equations of transformation, equations 9.4, do not contain time explicitly, okay? It will be called restricted canonical transformations. Again, in class, we're mostly working on canonical. The last term on the right in equation 9.11, that's this. This equation here, the last term on the right, contributes to the variation of the action integral only at the endpoints. It would therefore vanish if f is a function of qpt or qpt. Variation at endpoints. Not f q p t or q. I should put nor qpt. or any mixture of the phase space coordinates since these have zero variations at the endpoints. Farther, with the equations of transformation, equations 9.4 and the inverses f can be expressed partly in terms of the old set of variables and partly of the new. Indeed, f is useful for specifying the exact form of the canonical transformation only when half of the variables beside time are from the old set and half are from the new. It then acts as they were, so f, as a bridge between the two sets of canonical variables and is called the generating function of the transformation. So this is the generating function. So what I shall do, I shall take a break. We got to that part. And perhaps tomorrow I'll come in and we'll look in more detail at what the generating function does. So, seems like a slow night. I'll look for you all tomorrow, if not another day next week. Hope you all enjoy it. See you all next time.